it's not that we are not, when we can make accommodations for students, we can, but you may not know that we actually don't even get access to the permission system until after the first week of classes. So they don't even generate us the codes. My codes for adding classes don't show up until after, like Friday afternoon, the first week of class. So you can ask me for a code or any other professor basically, but we just don't even have them. It's entirely run by the computer for the first week. So if you ever wonder why people don't get back to you or they say, no, I can't do anything, we can't. We actually literally can't. All right, so we're going to talk about today 16.1 again, briefly, which is about, don't trip on my cord if you guys go that way. Vector fields. And then we're going to talk about 16.2, which is how do you do calculus in a multivariate setting when we have things like scalar and vector fields to deal with. So vector fields, I said last time, are just functions. So you can think of a vector field as a function f of x and y, or it might be a function of three variables, x, y, and z. And what that function does is it eats a point and spits out a vector. So you can think about it as attaching to every point in the plane a vector. So normally we write this as f1 of xy, f2 of xy, or in three variables, f1 of xy, f2 of xy, f3 of xy. And those guys are called the components of the vector field. So I think last time we plotted the example f of xy is equal to minus yx. And that was the vector field that sort of rotated around the origin, right? I think it looked something like vectors that look like this. And as you go out, the vectors get longer. I did not do a good job of that one. Here, and so on, right? So you can think of to each point in the plane, like the point 1, 0. The vector that gets attached is f of 1, 0, which is 0, 1. So the single most important kind of vector field comes from scalar functions. So if I write down a function, a scalar function, I have a scalar function f, say just of x and y in this case, because it makes our life easier, but I could have f of x, y, z as well. And I want to create the easiest possible vector field from that function. What can I do? It's an operation we already know to turn a function into vectors. Gradient will do it, right? If you write down, so this is what we call the gradient field of f is grad f. Scalar functions have sort of a built-in vector field, presuming that they have enough regularity to be differentiated, right? So every scalar function induces a vector field called its gradient field. So there's the relationship between f and the gradient of f is just like the relationship between a function and its antiderivative. So in one variable, in basic one variable calculus, if it's the case that g prime is equal to f, if I take the derivative of g and I get f out, g is the antiderivative of f, right? G's derivative is f, so g is the antiderivative of f. In our setting, we basically can say the same thing, except we use slightly different words. If the gradient of f, so if I have the relationship that some vector field f is the gradient of a scalar function little f, we say f is an antiderivative of the function capital F. So f is still an antiderivative because we still undid a derivative, right? And we call it the potential function. For f. So when I say potential function, I mean an antiderivative. If I give you a potential function, you take the derivative to get the gradient field. If I give you a gradient field, you're faced with a harder task. So one of the things that almost everybody has in their heads from one variable calculus is taking derivatives is easy. You get a pile of rules, right? Chain rule, the product rule, the quotient rule. It's just grinding to do derivatives. Integrals are hard. You have to use all this technique, U substitution, partial fractions, integration by parts, trig substitution. So you should expect that the same relationship is going to hold here. If I gave you a potential function, its gradient field is easy to compute. If I give you a vector field, if it even has a potential function, recovering the potential function is significantly more complicated. So I want to talk about that a little bit here. So let's look at two examples. Example, compute the gradient field of f of x, y, z is equal to x times the cosine of y over z. Now, there's nothing fancy in what I've asked you to do here. We already studied the gradient. I know how to take the gradient of a function. The gradient of f is equal to df dx, df dy. Since this is a function of three variables, there will be a df dz as well. So I can write down cosine of y over z minus x times the sine of y over z times y, or 1 over z. And minus x times the sine of y over z times y over z squared with a negative out front, right? That would be the gradient field. You know how to do this already. You just calculate a gradient. Now I'm going to ask you an opposite question. Let's see. I'm going to give you a vector field. So this is another example. And the technique I'm going to write down now is going to be studied later on in this class in detail and also in 244, if you take 244. It's called the method of partial integration. So I'm going to write down a vector field, f. And f is going to be, let's say, the vector field 2xy plus 1, comma, x squared plus 1. And I have two questions now. So I just gave you a vector field. You should have two questions. One, a question that is not immediately answerable. Is there an f? Is there some function f so that the gradient of f is equal to capital F? We cannot yet answer that question. How do I even know if I look at a vector field if it even has an antiderivative? So the answer to this question in this case is yes, because I thought of a function and I took its gradient and I wrote the gradient down. Right? So this particular one does. But characterizing the functions that do have this property, vector fields that come from potential functions, is one of the central questions of physics, engineering, and applied math. When do I know that I can do this? And if I can't, can I adjust the vector field so that it does come from a potential function? Right? And the second question is, if it was true that there is such an f, how do I find it? 2. If there is a grad f equal to f, how do I find it? And the answer is something I call, anyway, the method of partial integration. So I'm going to walk you through this just as a way of showing the relationship between derivatives and integrals in the context of potential functions and their gradient fields. So if it was the case that f was equal to grad f, then that would mean that the currently given vector field f here, which is 2xy plus 1, comma, x squared plus 1, would have to be equal to df dx, df dy. That must be true. If such an f existed, this is how you would have gotten the vector field from it. Well, that gives me a system of two equations. df dx is equal to 2xy plus 1, and df dy is equal to x squared plus 1. So what I'd like to do now is, well, I mean, if I know functions, if I know the derivative of f with respect to x is equal to this, can I find f? How? I could take the antiderivative, but I have to be careful. So if I took df dx is equal to 2xy plus 1, and I integrate both sides, I'm going to get f on this side. I'm integrating with respect to x. I'm undoing this partial derivative. So it's almost like a partial integral. F is equal to, okay, the integral of this with respect to x is x squared y plus x, because the integral of 1 with respect to x is x, plus c. Is it c? Sure. What sort of objects does d by dx kill? Anything in terms of y. Anything in terms of y. I could put an arbitrary function of y right here, and when I took the derivative with respect to x, it would vanish. So it's not just plus c. It's like plus c, which is a function of y. It might just be a constant, but it could be something else too. Because d by dx of a function of y is 0. So this is a partial integral. Right? We have to account for the fact that what we're doing here is not a derivative, it's a partial derivative. Okay, so now here's what we know. We've got our candidate for f. F is equal to x squared y plus x plus some function c of y that I just don't know. But there's information I haven't used yet. I know what the derivative of f with respect to y is. So schematically, you can think about this as, we had the function f. If I took d by dx of f, I got 2xy plus 1. If I took d by dy of f, I got x squared plus 1. So we started down here, and we undid the d by dx and got that function. So now I could take this object and take its derivative with respect to y, which will be x squared plus 0 plus c prime of y. I don't know what that function is, but if I took its derivative, it would be c prime of y. And these must be equal to each other. They have to be. If that was f, this is one way of writing down df dy, but I already knew what df dy was. df dy was given to me in the statement of the problem. So that gets us the equation. Oh, so it must be the case that x squared plus c prime of y is equal to x squared plus 1. What's c prime of y equal to? 1. C prime of y is 1. So what's c of y? This is just a regular integral now, right? It's just a function of y. So if I integrate it with respect to y, I get y plus c. Do you like initial conditions of your physical problems?
Yeah, but I hate writing the plus C.
You got to write the plus C. This is what tells you what the system does, right? The plus C tells you which particular answer solves the particular question you're solving. Right. So that means, well, now we know C of y, so it must have been the case that the general family of potential functions that created this gradient, and we can verify this. So now the claim is, after having walked through this process, that it must be the case that f of x and y is equal to x squared y plus x plus y plus possibly an arbitrary constant. And then you can just check, is df dx equal to 2xy plus 1? The gradient of f is equal to 2xy plus 1 plus 0 plus 0. And then the derivative with respect to y is x squared plus 0 plus 1 plus 0, which is exactly the field that we started with. Recovering potentials from fields is tricky. Unfortunately, it's also really useful to be able to recover the potential function from a gradient field. Okay, so we're going to revisit this method. I'm not going to put more examples in right now. I know this probably seems kind of mystifying to some of you. It's a method. This actually you could just think of as an algorithm. Start here, integrate it with respect to x, differentiate your answer with respect to y, and compare it to what you already knew that thing was, and then solve for the missing function. The bigger issue, I think, is how on earth do I answer that question? I can only do this if that statement is true. If there was no such f, I can't undo this. And unfortunately, many times what we want to work with in practice is fields that are gradient fields, fields that have potentials. And so it's a central concern to figure out when I can undo a gradient and get a potential function back from it. So the last thing we'll talk about before we move on to the next idea here is the geometric ideas that relate potential functions to the gradient field. And so this is just going to be a sort of a schematic picture. Suppose that you have, so this is sort of geometry. Another reason why these things are used. If you have f of x and y is equal to some potential. And you could think about this as electric potential. You could think about it as representing temperature. You could think about it as representing pressure. Then you could set up the level curves of f. But level curves of f, when we are thinking about it as a potential function, are called equipotentials. In various fields, these are called isotherms, isobars, so temperature, like lines of constant electric potential, I guess, would be the way, like, yeah. I guess I'm out of physical quantities for level curves. There are more. And so if you drew a bunch of those guys, you would get something like this. Oh, maybe here is, this is the place where all the z values were equal to 1. And here is the curve on which all the z values were equal to 2. And here is the curve on which all the z values are equal to 3. Remember that way you find level curves is you set the function equal to some constant, and then you draw the plot. Do you guys remember how the gradient field interacts with level curves? Or how gradients and level curves are related to each other? What was it? They are?
Steepest descent.
Okay, yeah, that's what so it tells you steepest descent, but geometrically, what's the relationship? They were perpendicular to each other, right? So if I had a bunch of equipotentials, I can actually, without computing the gradient, I can tell you the direction the gradients point. Computers do this very quickly. It can take a potential function, very quickly generate a bunch of level curves, and without computing a derivative, it can tell you the vector field that describes the gradients must look like this, because the gradient field is perpendicular to the potential field. So the potential field, the potentials, the equipotentials, force the structure of the gradient field. They force it. So what I'm trying to remind you here is the equipotentials are perpendicular to the gradient field. And we have one more bit of information, which is if I imagined for a second that I started with a potential function, the potential function basically forces the structure of the gradient field. And once you know the gradient field, you know, say if this was an electric field and I dropped an electron in, you know exactly the path that that electron will follow. If it's measuring the velocity of some fluid or air and you let something go subject to the motion induced by those flows, you know exactly what the trajectories are going to be. The trajectories must follow the gradient. The gradient tells you what direction things must be moving, the velocity. So if you track those, you'd end up with these curves that go through it like this. Let's see, maybe this one you go out this way and then up like this. These guys are called flow lines. So flow lines track in a gradient field how an object would move, what the trajectories of objects moving subject to that field would be. Again, electron dropped in an electric field. What is the natural path it would take if you don't introduce any outside forces to it? So this relationship between flow lines, equipotentials, and gradient fields is a sort of fundamental set of relationships. And it's weird, actually, I think, and powerful to think, all I need to be able to do is measure the potential. If I tell you temperature on a map, I can tell you how heat is flowing and what pathways it's flowing. That's powerful, right? This type of mathematics was invented specifically, actually, to study electric potential, right? So the electric field lines, like this, these are the electric field lines that are induced by the curves of equal electric potential, for example. So a lot of this is like why these things were originally invented was physical. And so the analogies I'm going to be using when I build these things are going to be physical. So for those of you that don't like physics, there's not really much to do here. The easiest way to understand what's going on is thinking about these things as fluids or electrical fields. And the motivation for the mathematics comes from those as well. So I will be using those as analogies as we go through into the later sections. Okay, so let's talk about 16.2. So 16.2 is about a type of object called a line integral. The idea is I want to set up a notion where I can take things like scalar potential functions and the gradient fields and do calculus with those functions. But in order to do that, I'm going to be doing integrals over curves. Integrals over curves. And that means I'm going to remind you how the basic parameterizations work. Because we're going to be working with integrals over curves, we should remember how to parameterize a curve. So basic parameterizations. I apologize, this is not exciting, but is necessary. And I think since we haven't done this in, the middle of last quarter, I think is when we studied this. There's three basic cases we need to deal with. The first is, how do I write down the parameterization of a line segment between 2 points? So if I gave you a point P that had coordinates x naught, y naught, and z naught, and I gave you a point Q that had coordinates x1, y1, and z1, and I want to write down a position vector, r of t, which is x of t, y of t, and z of t, that describes the motion from that point to that one for some sort of values of t. This is the goal. I want to produce a parameterization of the line segment connecting those 2 points. Not a function, a parametric description. X of t, y of t, z of t. I'm thinking about, I need to describe the path of a particle traveling along that line segment. These are not unique. There's lots of different ways to do this, but there are standard parameterizations. Does anybody remember how to do this one? Okay. Good. Yeah, that's exactly it. So the general form of this one is you can always write this case down as R of t is equal to your starting point, your P, plus the vector connecting P and Q times T, and then T just goes from 0 to 1. In coordinates, if you write that down, it would be okay, geometrically what you're doing here is you're going to P with that vector, and then you're traveling in the vector pointing towards Q from P, and then just stretching it out until you actually get to Q. So there's P, here's Q out here. This picture that we've drawn that's the vector P, this is the vector PQ times T. That lands you here. When T gets to 1, then you're all the way there. Because this vector is P plus PQ. Or you can memorize like R of t is equal to x naught, y naught, z naught, plus x1 minus x naught, y1 minus y naught, z1 minus z naught, t, where t goes from 0. It's easy enough to check this holds, because if you put t is equal to 1 in here, the x naughts cancel, the y naughts cancel, the z naughts cancel, and you're left with x1, y1, z1 is the output point. So this will get you exactly from P to Q. So this is the sort of one you should be able to do basically instantly. If I write down something like, find the line segment from the point 1, 1 to the point 5, 2, and you want to parameterize that line segment, absolutely the easiest way to do it is to write down R of t is 1, 1 plus 5 minus 1, 2 minus 1 t, and then you can write t goes from 0 to 1. That's the standard way to parameterize a line segment. You don't even need this step. Just write down 1, 1 plus 4, 1, 2. Okay, second basic set of curves we need to be able to deal with are not line segments, but chunks of circles. Case 2, chunks of circles. I guess chunks is not really a mathematical word. Arcs of circles. So if I gave you, instead of a line segment between 2 points, I say something like, I would really like to know how to parameterize the arc going from 0, 2 to minus 2, 0 of a circle. What should I use? This is easy. Johnny? Yeah, polar coordinates, right? Do polar coordinates to it. If you're living on a circle, use polar coordinates. There's a million ways to parameterize arcs of circles. If you want to do a standard parameterization, just use polar coordinates. So R of t is equal to 2 cosine t, 2 sine t, and then just figure out the range that you need for the t values. I guess t goes from pi over 2 to pi here. Third case. Y equals f of x. That is the case of functions. So if I gave you a function to parameterize, for example, I don't know, about y is equal to x times 2 minus x squared, where x goes from 0 to 2. I'll plot that for you. So that function goes through 0 from below, and then it comes down and bounces off 2 and then goes up. So the piece of the curve I'm asking you to parameterize looks like this. That yellow segment right there. I really need to have an R of t is equal to x of t, y of t. What do I do? I don't even see where to get a t from. If only I had an independent variable. What should I let x be equal to? T! Wow, that's pretty easy. X is t, and then what should y be? f of t. T times 2 minus t squared. That's the easiest of the parameterizations, right? Graphs are very easy functions. So in this case, r of t would be equal to t comma t times 2 minus t squared. So there are 3 basic ways of parameterizing curves, just to remind you. And the reason that we're parameterizing curves is because the problem that we're going to be considering now is the following. So here's our first problem of integrating functions in the context of vector calculus. So here's our first basic question. I give you a curve sitting in the xy plane. So here's x, here's y, and I give you some c of t, or r of t running around inside here. So here's r of t. R of t, some sort of curve sitting in the xy plane. And then I have a function that sits over the top of it. So I'm starting with the function z is equal to f of x and y, but I'm going to restrict the function so that the only inputs it sees come from the curve. So you can imagine it's like the height of a roller coaster track or something, right? It can only see points that have the form r of t. So right there, there's an r of t. F can look at that point and tell you, oh, that's f of that height from here to here is f of r of t. That's what f does, right? It looks at a point on the curve and tells you how high up to go. So if you did that at every point on the curve, I'm not going to do them all, but you can imagine it's basically going to build you like a set of fence posts to tell you how high the curve was at that point. And if you connected them all, you would get sort of this path that sits over the top of the curve. You can think about it sort of like a roller coaster track, right? So f sits inside of a large, this is a surface, but we're just saying, oh, well, I don't care about the whole surface. I only care about the part that sits over the curve. So here's the first question. I would like to know that area that's between that curve, the yellow curve, the roller coaster track, and the curve that it sits on top of. If I think about this as a fence or a shower curtain or something, I would like to know the area that's of this sort of curved surface. Area makes sense here because this is flat. If you think about it, the shower curtains fold up and are all wrinkly, but you could straighten them out and you could calculate the area. The area didn't change just because it got folded up on itself. Whatever this area is, if you could unfold it in a flat way, it would just be a flat area. It sits curved in space, but it's flattenable where that area would make sense. So our first task here is to try to figure out a definition that we could use for even calculating what I mean by that. So what I'm going to do is I'm going to isolate one of these rectangles. They're not really rectangles because they're sitting on curved surfaces. I'm going to say that this bit right here kind of looks like if I took it off of this xy plane and I wrote it flat out for you like this. That's this one. Kind of looks like this. That's a pretty straight looking piece of curve right there. So this is pretty straight down here. So this is kind of almost a rectangle. If it was a rectangle, how would I calculate its area? Base times, okay, that's pretty good. Base times height. There's base. Here's height. And if we were back in the land of calculus 2 when you first learned the definition of an integral, the way that you would calculate that base times height is you would pick some point in the base. Normally, when we learned it the first time, this is called like xi or x naught or x star, some point that was selected down here. In our case, because this comes from a path, I'm going to call it r of ti. Some time was selected. I feed it into the curve. It tells me the value of the point. And if I want to know the height of the rectangle, I need to know how tall that line segment is right there. Well, how tall is it? How do I find it? F of it. Yeah, so that height right there, that height is f of r of that point that we selected. Okay, so we're making some progress here. Now we know that the area of that rectangle is about equal to the height, which was f of r of ti, times, oh man, the base. So the length of that purple segment. The length of the, well, I mean, what is the base? Right? It's the length of the base. Damn. The length of the base. So I need to know how long that purple section is. Do I have any sort of notion for figuring out how long a piece of a curve is? Arc length. Okay, so this down here is going to be a delta S, a little tiny chunk of arc length. And that means that the area of that rectangle, even though it's curved, if I could sort of pretend it was straight for a second, it would be about equal to the arc length of the bottom times the height. Okay, so now we're getting places. So that would say that the area of our little rectangle down there, the area of that rectangle is approximately equal to f of r of that value that we chose from the bottom times a little bit of arc length. And if I wanted to know the area over the whole curve, I can just imagine doing that over and over again. Just break it up into, there's a delta S, and there's a delta S, and there's a delta S. Take your curve, chop it up into these pieces that approximate the length, and then multiply by the height of the function. And that's going to say that if you add them all up, the total area should be approximately equal to the sum over I of f of r of ti times delta s. You guys told me base times height. And through the magic of integrals, by taking a limit as the delta s gets smaller and smaller, we're going to take, for our definition of this integral, and I'll take the limit as delta s goes to 0, and what we're going to get is that area is equal to the integral over the curve, that symbol means take the integral over the curve, of the height of the function times the width of the rectangle. So this object right here, the integral over the curve of f ds, is the definition of integrating a scalar function over a curve. And what we built this, why it was just by imagining this exact picture. Base, which is delta s, times height, which is f. Base times height. If you want to calculate it, man, if only I had a way to figure out what ds is equal to. Because I can integrate from a to b. This is supposed to be r. Sorry, I don't know where the c came from. R. It's the r from the picture over here. F, eating points from r of t. And is there a way to calculate ds in terms of the curve? Do you remember how to do that? What is ds equal to? What is our unit arc length? X prime squared plus y prime squared. It actually will work with z prime squared as well. Is there a more convenient, dt. Is there a more convenient way of writing that? Okay, so I'm going to observe that in calculations, a more convenient way of writing this is to write that this is the magnitude All right, so we did this when we did the vector calculus. We were doing arc length. This is the length of the derivative vector, right? The derivative of r is x prime y prime, and its length is x prime squared plus y prime squared inside of a square root. So this is a convenient calculation representation for what ds is. And so when we want to calculate this integral, we write the length of r prime of t dt. And if the two lines just mean the length of the vector. Okay, this thing right here, that is our definition. It's a definition of the function. So the interpretation of it is, one interpretation of this is, I can think of this integral as representing the area of this fence. I got this twisty, bendy fence with the height of the fence changes continuously over its bottom, but the area of the fence is this. This is the untwisted version of the shower curtain. So that's important enough, I'm going to write the whole damn thing again. This is a definition. Definition. Given a scalar function f and a parametrized curve are the path integral of f over r is the integral over r of f ds, which is the integral from a to b of f of r of t, length of r prime of t. A natural question some of you are probably like just waiting to pin me with is, okay, but that doesn't make any sense if I've got a path in R3. So does this still make sense in 3 variables? You can't draw the picture with the fence anymore if the curve is in 3 variables and you've got integral of f. And the answer is, the way to think about what this is actually computing is, if this thing right here was a density function, this is probably the most natural way of thinking about what happens in 3 variables. If that was a density function, and this was measuring arc length, density times length would be mass. So this is an integral that will compute from a density function what the mass of the curve happens to be. Okay? That is probably the most natural interpretation of what's happening here. If that was density and you were integrating density over a curve, this would tell you the sort of linear, like that was a linear density. Well, density times length is equal to mass, and so you would be calculating the mass of the field, or the mass of the curve. Right, so this dude right here, oh, actually, there was another interpretation that the last class liked, or somebody in the last class liked better, is if I took this, say f measured temperature, any scalar quantity could be an f here. If f measured temperature in some, like in R3, say, and you had a curve that was twisting through R3, this integral, if I divided by the length of the curve, would tell me the average value of the temperature on that curve. So you could take this integral and divide it by the length of the curve, and you would get the average value of f. So there's a lot of ways to interpret what's happening here that are not just a graph of a roller coaster, some 4-dimensional roller coaster track. Don't try to do that. Okay, so what remains to do now is, well, that's great. This gives us a way of working with scalar functions. This is a method that works on potentials. If I give you a potential function, and I have some path running around inside of R3 or R2, and I want to integrate the potential function over the path, I have a really nice definition to do that and a calculation method for extracting it. What I don't yet have, and this is the real meat of this chapter, is the other picture, which is, what if I don't have a scalar function f? What if I have a vector field instead? And the basic motivating question for the next type of integral, which we're not going to do today because there's no way there's enough time, is the following. If I gave you a vector field, so you can imagine a gravitational field or an electric field, I give you a vector field. And in that vector field, I prescribe the motion of some particle. I could ask, how much work was done? If you imagine that this is a force field, so these are all forces, F is equal to force, how much work was done moving the particle through the force field from that position along this path until you got back here? That is the basic question that we're going to try to answer in the next section of this chapter. So, I think probably everybody remember, what is force? How do I calculate work? What?
Integral of x.
Oh, no, that's linear. No. We're actually going to build this up. So the version of it that you learned, I'm going to give you 3 different versions of work you should remember. There's the I learned work the first time, FD. Right? There is a force. It points in the same direction as I'm moving. There was a 10 Newton force, and I slid it 10 meters, so I did 10 times 10 units of work, which is Newton meters. And then you learn the sort of fancier version where maybe the force varies and you integrate it. But what if, okay, so here's another question. What if the force and the displacement happen in different directions? What if I have an object and I displaced it by a vector d, and the force that was applied to it was not acting in the same direction as displacement? Okay. Oh, cosine.
Or like electric.
Oh, no. I'm going to actually show you guys when we derive this that actually it's just f dot d. Cosine has nothing to do with it. Except for the fact that dot products are built out of cosines, right? Okay, but the problem is that means that, okay, you can actually already see where this is going to go. I could calculate work if I had a consistent displacement vector and a consistent force vector, right? If the force vector didn't vary and the displacement vector didn't vary, I could calculate the work. So if I don't know, happen to be moving something on a curved path, if only there was a way to decompose it into little straight pieces. Like maybe what I should do is I should say, oh, well, if I was right here, the curve between these 2 points is about equal to the line segment that connects them. And so the work done, if I call this the vector d, and this vector up here is the force vector at that particular position, then the work done moving along this little tiny chunk of the path is just f dot d. So if I had some sort of tool I could use to decompose my curved function into a bunch of straight pieces, I could just apply this idea over and over and over again. And that would let me calculate the work on the whole path instead of just on a straight line segment. That is basically where we're going to go in the next part of the class. Is we're going to build this integral, which kind of ridiculously is called a line integral instead of a path integral. I don't know why, because you're not integrating over a line. But if I say path integral, I mean a scalar function over a curve. And if I say line integral, we're going to refer to an integral of a vector field over a curve. So next time we will build the integral that tells us how to calculate this situation. Work done on a particle by a field on a curved path through it.